Have you ever looked up at the night sky and just wondered, how does it all work? You see the planets wandering around up there, and it looks pretty random, but it's not. They're rules, a kind of hidden cosmic code that governs their every move. And today, we're going to crack that code.
Now, the answer might seem obvious to us today, but for most of human history, our best guess was completely, and I mean completely, wrong. So let's dive into a mystery that stumped some of the greatest minds for thousands of years. How do planets really move?
All right, our story begins with an idea of the universe that was beautiful, it was elegant, and it was totally wrong.
You see, for centuries, pretty much everyone, from Aristotle to Ptolemy, believed in a geocentric model, the idea that Earth was the center of everything. Makes sense, right? But then, guys like Copernicus came along and proposed this radical new idea, a heliocentric model with the sun at the center. Now, this was a huge leap forward, but even this new model had a major problem.
The big hang-up, the one assumption that held everybody back, was this idea of perfection. The heavens had to be perfect, and what's the most perfect shape? A circle, of course, but here's the thing. When they actually tried to match their observations to these perfect circular orbits, the math just never worked. It was always a little bit off.
And this is where the German mathematician Johannes Kepler enters the story. Kepler was obsessed with the data on Mars. Its path in the sky was just weird. It refused to fit into a nice, neat circle. Mars was this stubborn, cosmic clue that just wouldn't be ignored. And it was the key to unraveling the whole thing.
And that brings us to Kepler's first mind-blowing breakthrough. He called it the law of ellipses. And with it, he basically shattered an idea that had stood for 2,000 years.
Kepler's brilliant insight was that the orbit wasn't a perfect circle at all. It was an ellipse. You could think of it as a stretched or a squashed circle. Now that might sound like a small change, but it would completely rewrite our map of the solar system.
So what exactly is an ellipse? Well, instead of having one center point like a circle, it has two special points inside called foci. And this is the crucial part, the sun isn't at the exact geometric center of the orbit. It sits at one of those two foci.
And this, right here, is Kepler's first law. Every planet's orbit is an ellipse with the sun at one of its two foci. This immediately explains why the distance between a planet and the sun is always changing throughout its year. Sometimes it's closer, sometimes it's farther away. And we even have a cool term for how stretched out an ellipse is. We call it eccentricity. So a perfect circle has an eccentricity of 0. The more squashed the ellipse gets, the higher its eccentricity becomes.
Okay, so Kepler figured out the shape of the orbits. That's a huge deal. But what about the speed? Are the planets just cruising along at a constant velocity? Nope. And this brings us to his second law, which is just as cool, the law of equal areas. I want you to imagine a line, like a giant cosmic rubber band stretching from the sun to a planet. As that planet moves, the line sweeps out an area, kind of like you're painting a slice of a pie. Now, Kepler's second law says that for any equal amount of time, say 30 days, the area of that pie slice is always the same. So for that to be true, when the planet is close to the sun, the slice is short and fat, meaning the planet has to move super fast. And when it's far away, the slice is long and skinny, so the planet has to be moving much slower. This gives us two key points to remember for any orbit. You've got perihelion, that's the point where the planet is closest to the sun and it's moving at its absolute fastest. And then you have aphelion, where it's farthest from the sun and moving at its slowest. So the planets are always speeding up and slowing down in this perfectly predictable rhythm.
All right, so Kepler had the shape and he had the speed, but he was sure there was something deeper, a kind of mathematical harmony that connected all the planets together. This nagging feeling led to his third and maybe his most incredible law, the law of harmonies.
Kepler's third law uncovered this absolutely beautiful relationship between how far a planet is from the sun and how long it takes to orbit. He figured out a precise mathematical formula, but the simple version is this. The farther out a planet is, the slower it moves, and the longer its year is. It's this simple, powerful rule that tunes the entire solar system like a finely crafted clock.
So these laws were discovered over 400 years ago. Why do we still care? Well, because they are basically the operating system for our solar system, and we use them literally every single day.
For instance, we apply these exact same principles to understand and predict the orbit of our own moon as it goes around the Earth.
And because we know the moon's path so precisely, we can predict solar and lunar eclipses down to the second, centuries from now. How amazing is that?
And here's the best part. It's a beautiful full circle moment. We use Kepler's laws today to calculate the perfect time to launch our spaceships to Mars, the very planet whose stubborn orbit started this whole revolution in the first place.
So the takeaway here is just huge. Every time you predict an eclipse or use GPS from a satellite, or we plan a mission to another planet, or even calculate the path of a comet, it all rests on the foundation that Kepler built. His 3 laws are absolutely essential to modern life.
And maybe his greatest legacy of all is this. Kepler's work gave us the how. He laid out the rules of planetary motion. And that's what allowed the next genius in line, Sir Isaac Newton, to come along and figure out the why.
Which leaves us with one final fascinating thought. Kepler gave us the blueprint for the solar system. He described the dance perfectly, but he didn't know about the force leading the dance. He knew how the planets moved, but not why. So what is this unseen force that governs the whole cosmic dance? Well, that's a story for another time.